So although we have problems like this, we've also done sheet, but they're not going to ask us about the infinite sheet. They're very likely to ask us about multiple infinite sheets. Perhaps a positive sheet and a negative sheet, and use Gauss's law to determine how the electric field looks both between these two infinite sheets and on the outside of these two infinite sheets. You'd have to be careful about what you would do with your Gaussian surface. You could not choose a Gaussian surface like this and probably be likely to get the answer you're thinking you're going to get. You have to understand the limits of what your Gaussian surfaces can provide and be aware of how you'd have to draw your Gaussian surfaces to successfully communicate electric field. So there's quite a bit we have to do and ways to apply Gauss's law. For right now, though, we're going to kind of stay focused on where we've been. I want to look at one more three-dimensional example, and this is it's a cylinder. So to understand the cylinder example, you need a cylinder. So the idea is to have a solid cylinder. And to draw that's not easy, so just be patient with me for a moment. So I have a very long, nearly infinite, solid cylinder of charge density rho. So the cylinder is, of itself, a very long cylinder. And we'd like to determine what the electric field is both inside the cylinder and outside the cylinder. Again, another classic style of Gauss's law question. The solid cylinder has what I hope you notice to be a very clear and relevant symmetrical surface. If it's a cylinder that goes on infinitely in all directions, we can probably make some accommodation for what the electric field probably looks like coming from the solid cylinder. The way I've drawn this might not have been perfectly suitable for how we're going to have to analyze it, but I don't think it's terrible. And I hope you all realize that there's probably going to have to be some reference paid to the radius of the cylinder versus the location that we are going to be away from the center of the cylinder. Now, to put a finer point on it, I'm going to kind of identify. I don't like where I drew the R, so let me move it up a little bit so that the radius is not in the way of what I'm about to draw. Let's have this blue line represent the center of the cylinder. And I've kind of drawn a cross section, but you guys do realize that the cylinder actually continues in this direction. You guys all okay with that? So if we want to determine the electric field outside the cylinder, we would of course have to have a Gaussian surface that has a distance from the center of the cylinder that is greater than capital R. Agreed? So just like the infinite line, we're going to use something that exploits the symmetry of this cylinder. Now, I don't want to make this picture. I'm looking at something like, let's see if I can do this. Does that make sense? It's a cylinder around the outside of my cylinder. Everybody okay with that? If not, speak up now. I'm going to use lowercase r to be the radius of the external cylinder. I have to be done here. First, obviously, our Gauss's law has two sides to it. There's the amount of charge enclosed on the left side. We'll have to deal with that. And then there's going to be the flux portion on the right side. I believe it's easiest to deal with the amount of charge enclosed first. I'm going to define the size of my cylinder to have a height of h. And this side's going to have an area of pi r squared. That all okay so far? And that means the external area of the cylinder is going to be 2 pi r h. All those things okay so far?
What's that, the error, the error being covered on the board?
So we're just talking about the area of that side of the Gauss's surface. It's a can, you know. Now, it is cutting a cross-sectional area of the cylinder. That there's a cylinder here where the Gaussian surface is kind of cutting into it. Somewhere like right there, where our Gaussian surface and our actual cylinder are lined up. Surface inside my can. And it's hard to kind of see this three-dimensionally, which is why I'm trying to make sure we're buying into it together. Because if not, I'm not sure that was making it clear, we are enclosing a piece of the cylinder that starts here and goes along the length of the cylinder. Like there, and there, all the way to the other end of the cylinder. This is how much of our charged cylinder we're kind of capturing inside the can. I need to know what the volume of that portion of the cylinder is because it's the volume of that portion of the cylinder that is our enclosed charge. So if you don't know what the volume of a cylinder is, allow me to enlighten you. This is going to be the volume of the cylinder of charged material that is stuck inside the can of my Gaussian surface. Notice the switch to big R here because the radius of the cylinder is capital R. So I am capturing this much of the surface area, and times h gives me how much of the charged cylinder is inside my Gaussian surface. I need the volume because enclosed charge is going to be rho times that volume. Now, if you look back at your notes for the infinite line, we had lambda times the height. Do you remember that? Can you look at your notes and see that? That was how much charge from the infinite line was trapped in our Gaussian surface. But I can't use a length here. I have to use a volume here because I'm capturing a cylinder worth of crap. So instead of having lambda times L, I have rho times pi r squared h. Because I'm capturing a cylinder worth of stuff. That all okay? Am I talking beneath you, or am I keeping you all where you're supposed to be? I had a feeling. Make sure you get it out.
So charge enclosed equals, is that the circle with the line volume times volume, or is that P?
You're gonna have to say that again.
Okay. Where it points to the volume. Where charge enclosed equals P or something else?
This is the symbol rho for density. It is volumetric density. Getting back to this, I'm trying to put all this together, but this is the hard part, convincing you of the geometry of what we're looking at. So the enclosed charge has to be how much of the charged cylinder is inside the Gaussian surface. So how much? I need the volume of the amount of the charged cylinder inside my Gaussian surface. I define my Gaussian surface to be H big. Therefore, the amount of the charged cylinder inside my Gaussian surface has to be big as the cylinder inside the Gaussian surface, which has got to be pi r squared h. Times rho gives us a charge, so this is going to be rho pi r capital R squared h. And that must also equal epsilon times the flux. Whew. Great, now we have to do the flux part of this. That part's actually relatively easy if I can convince you of all the other stuff. So let's do this part. Stuff it. Make that a little smaller. Get that out of the way. So let's talk about the flux now. I foresee that there are 3 different surfaces to the can of my Gaussian surface. There's the top, there's the bottom, and there's the sides. For the same reasons why the top and the bottom had no flux last time, I'm going to, by just default, say that we can probably throw out the top and bottom this time. And if you don't know why, it's, bet you wish we were talking about class rank now. We get 0, 0, and we're left with integral of E times dA. And I've already dealt with the cosine, so I don't even have to list it. Yes, sir?
If this is like an effort cue, do we have to draw all of these visuals?
Generally, no. Generally, the visuals are drawn for you. The last time this one was on the AP exam, which was just a couple years ago, they had 2 different pictures. One of them had the Gaussian surface inside, one of them had it outside. They gave you the Gaussian surface for this one. They don't always, but if it's a difficult visual to draw, they'll usually give it to you. Or they'll have something like this. They'll have... All right, so believe it or not, we're near the end of this, so I don't think I have much more to do here. E is going to be constant everywhere around the outside of that cylinder because it's equidistant from the center. And dA is just going to be the surface area of the side of the can, of the Gaussian surface. So the surface area of the side of a cylinder is just going to be 2 pi little r times h. That is the surface area of the side of our can. Circumference times height. We all good there? That's good because now I can use this to show that the electric field outside of a charged cylinder is the same as a line. Rho pi r squared h equals epsilon naught times 2 pi r h times E. Get E all by itself. And boy, this is a mess. At least the h and the pi cancel. Let's get rid of those. And I'm going to have that E equals, well, there's going to be this 1 over 2 pi epsilon naught. We got that thing. Let's get that to the side. Times rho r squared over r. Now, last time we just had lambda. Just lambda's on top. This time we have rho r squared. It's still just the charge density. This is turning the volume charge density into a linear charge density. Just treating the whole thing like it has a linear charge density because we're outside of the cylinder. But I'll wait for everybody to kind of get here because I see people studying it. I didn't make a mistake. Yes, sir?
Didn't you cancel out the pi, so why is there a 2 pi in the 2 pi epsilon?
Did I cancel out both pi? Yeah, I did. Good. Good. No pi. Fine. Screw you, pi. We don't want you in there anyways. There we go. That's right. Screw you, pi. Didn't want you in my answer anyways. Yep.
Sorry, I was writing down what you were saying. So we're making this into a linear density for us to look at?
No. I'm just saying that the last time we did this whole thing was the linear density.
Oh, okay.
And this time, this is like the linear density.
Okay.
Same units. I hope you all see that it is the same units. Rho has to be coulombs per meter cubed times meter squared gives us coulombs per meter. That's a linear charge density. Can I keep going? Interestingly enough, some people will write this a little differently. They will write this like this. They write this as 1 over 2 pi epsilon naught times rho pi r squared over r. And they do that so that you get this term, which looks exactly like the term we had for the charged line, where the pi is there. And this actually is the linear charge density for something that has spatial extension. They become equivalent because the pi is there. That becomes pi r squared, the cross-sectional area of the tube. So sometimes people will write it like this. The AP exam won't care though. So what we had before, just fine. And by the way, this isn't the part that matters. It's important that you get this because it should look just like a charged line because we're outside of it. Just like when we were outside the sphere, it looked just like a point. The issue to be made here is that we expect when we're outside of something like a charged sphere or a charged cylinder or in the future a charged slab that they look just like the infinitesimally things that we had before, a point, a line, and a sheet. They should always conform to the same things that we've seen already. The issue comes down to what happens when, too much, I'm just going to say that when we look at this, we're now talking about a Gaussian surface that is inside here. Like that. So we are inside the cylinder. So what we're looking at is what happens when we are inside the cylinder. So when, here's our cylinder. We want to talk about maybe a Gaussian surface that is inside. It's hard to draw this down the length, but I think we can imagine there's an extension here, that this is coming out of the board towards you. Is that all good? Because it's going to be hard to draw that. But I can, I'm not even going to. R is less than capital R. Now the first thing that happens is our Q enclosed changes. We're now enclosing a little bit of the cylinder. The volume that we're enclosing now is pi little r squared times h. Because we're not on the outside of the cylinder, we're on the inside of the cylinder, so we're enclosing a smaller amount of this charged cylinder. That all okay? Because nothing else really changes besides that. That's the only thing that really changes. We're still going to set this equal to epsilon times the flux. And we're still going to have the flux be E dot dA. And we're still going to take that flux and break it up into 3 sections. The top, the bottom, and the sides. And for the same reasons as before, the top and the bottom are both going to be 0 because there's no flux at the top and the bottom. They're still just perpendicular to the whole system. They're perpendicular to the direction of the electric field. None of that has changed. And so we're still going to get just epsilon naught times E dot dA for the side of our cylinder. And our cylinder still has the same shape, so that's going to be E times pi r squared h. All of that stays exactly the same, not pi r squared. 2 pi r, there. Still the outside of this cylinder. None of that's going to be different. It's just that now we're inside of the bigger cylinder, not outside the bigger cylinder. We have enclosed less charge. Now, solving this for E, cancel out one of the R's, cancel out the H, cancel out the pi. And we get this kind of, I don't know, I think it's kind of weird. We get 1 over 2 epsilon times rho times R. This is only good when R is less than capital R. But I want you to note it's linear again. I say again, but understand that if I wrote this as rho 2 epsilon, all of that is a constant times R. It's linear. The last time we had a linear one was the sphere, remember? The sphere was linear when we were inside the charged sphere. Now the cylinder is linear when we're inside the charged cylinder. Notice a trend? You should. We might see a similar trend in a charged slab. When we're inside the slab, the more charge you enclose, the bigger the electric field gets until you get to the outside of the object, and then it either is constant or it decays. This is the same kind of thing, and I'm not surprised by this. That the more you enclose charge, the stronger the electric field builds. But now the charged cylinder, I think I did a not a particularly good job trying to give us a good visual on that. But I hope you understand we're expecting that as you enclose more of this charged cylinder, you're going to be getting a larger and larger electric field. That the point here, I'm going to use that same color, the point here will have a smaller electric field than a similar point here, which will have a smaller electric field than a similar point here. But once I reach this point at the edge, I am going to see the largest electric field. And then as I travel away from this point, the electric field begins to decay immediately. Same thing with the sphere. Start at the center, no electric field. And as I get further and further and further away from the center, the electric field builds until I reach the edge, and then it starts to decay. Now, we've only been talking about the electric field, but you do understand we're going to have to eventually talk about the electric potential. But these things produce fields, therefore they have potentials too. And the potential inside here is probably interesting. Or at least maybe different than what we might expect. But I hope that all of you realize that no matter what, the potential here on, say, the edge has got to be less than the potential at the center. That if you can get into the center of this, you're fighting against an electric field, so the potential is continually rising as you get closer and closer to the center. That we can't mistake what the electric field is doing for what the electric potential is. The more you have to push against an electric field, the more the electric potential is going to continue to increase. That the hardest place to reach will be the center of the cylinder or the center of the sphere, because you're pushing against an electric field the whole time to get there. Now, that's a lot, and I get that it's a lot. So would you like something that is not hard? What if I could tell you that there are just some rules out there that I don't have to explain, that they are just the way they are, and all you have to do is know them. And I'm going to tell you the first one. Conductors are great. Conductors are really interesting. Because no matter what the circumstance is, no matter what you've been told or what you see, the electric field inside every conductor is zero. This is an absolute. There is no exception to this rule anywhere. No matter what's happening, the electric field inside all conductors is zero. Now you have to be inside the conductor, in the material itself. So if I have a conducting sphere, so the whole thing is one big solid piece of metal, solid all the way through, like the marbles you were trying to drop yesterday if you were in that class. The electric field inside here is zero, everywhere. And it doesn't matter what the situation is. If you're inside a conductor, the electric field is zero. So you could have a very strong charge right here, and another charge right here, another charge right here. Doesn't matter what your arrangement, no matter where you place this in space, inside every conductor, the electric field is zero. What's interesting about that is how is that possible? It's because of conductors. Conductors have the ability to reconfigure the charges in the material to cancel out any external electric field. This is why you have no signal in my room, by the way. This is called a Gaussian shell. Doesn't have anything to do with Gauss's law. But this room is surrounded by a metal gridded lattice. It's not solid, but look at the ceiling. You see what I'm talking about, right? That same thing is in the walls, because there's all the pipes in the walls for electrical and for plumbing and all that. There's a metal lattice that was put through all of the cement, the rebar. It was all interconnected. The entire room is surrounded by this electric shell, creating an electric field of zero. So the only charge in our room that we can experience is ones we brought with us. So your phone gets no signal here. This is why phone signal goes to zeros, because you're standing someplace where there must be a lot of metal around you. Now, that being said, consider what's really happening here. It's kind of interesting. Before I put this charge here, in our metal, and this is something else you'll need to know. In a metal, the negative charges are free to move around. The positive charges are tightly bound by each individual atom. Because the negative charges are free to move around, they try to get as far away from each other as possible. All negative charges repel. And because all negative charges repel, the outside edges of all conductors will contain all of the free-moving electrons. It's not just valence electrons. Metals have a lot of these loosely bound electrons that can kind of just move around from atom to atom. But because like charges repel, these electrons all move to the outer edge of your material. Now, with a circle, that will mean that they're all evenly spaced. If we're talking about a square or something with a corner, you'll get areas of higher concentration of these electrons and areas of lower concentration. This is why you have to be careful about certain shapes for metals. Some shapes will develop an increase in the number of electrons. The points of objects is what they're often called, which is why points tend to have areas of decay or areas where there's discharge happening. Lightning doesn't strike the middle of a tree. It strikes generally pointed areas of a tree. And similarly with lightning rods. Lightning doesn't strike the middle of the lightning rod. It strikes the pointed area of the lightning rod because there's higher concentrations of charges there. But with the circle, they're all going to be uniformly spread. If I bring a positive charge close to a conductor, it's going to attract more negative charges. So these charges will tend to move to the side of the circle where the positive charge has been brought. They will be attracted to that positive charge, which is going to reveal sections of the sphere where more positive charges are left over. This is called charging by induction, meaning I am creating a separation of charge. I'm creating a separation of charge in the sphere without touching it. Now, I have to say this before you leave. The red line represents the electric field from my point charge. The green line is the electric field created by this induced charge. It goes from positive to negative. In a conductor, it will always cancel out so that the electric field will be zero inside all conductors. It's unbelievable that this works, but it works no matter what. The only time it doesn't work is if you put a charge so big next to the conductor that the conductor breaks down. There's that many free moving charges inside a conductor, so all conductors have an electric field of zero inside. Bye-bye, folks.
It's exactly like you write that. You write it.
These are the symbols I've given before. This is not the first time. Perhaps make a little symbol chart. Lambda, used for linear density. Sigma, used for aerial. Never spelled this word right. It's not Ariel, the girl who lives under the sea. It's Ariel. I don't know if I'm spelling it right. It's air. Screw it. Not even going to try anymore. Surface density. Area of a two-dimensional shape. And this is rho, which is a volumetric density. It's the same symbol that you were supposed to be shown in chemistry for density. I don't care if you were or not. This is not my first time saying it. So, have a chart. Have a chart. Okay? I'm going to say the word rho. Call it like it is. When I write rho, write rho. You guys say that. Write rho. You should really say it. It's fun. It sounds like you're like got a speech impediment, but you don't. Write rho. I'm glad I'm recording that, so now I'm, somebody accused me of making fun of people's speech impediments. I am not. But it's kind of hard sometimes to picture what we're doing. So imagine this is a picture of the cylinder, but we're very far away from it. Would you agree that we're still looking at the same kind of electric field lines that are going to be parallel to each other and perpendicular to the cylinder itself? Does that seem not unreasonable as a means of kind of coming to grips with what we think the cylinder might be behaving like? And would it be too far-fetched to believe that if we look down the axis of the cylinder, that we would have electric field lines that would be similar to like the point charge, but in two dimensions like that? Does that also seem reasonable? So there's a certain symmetrical uniformity, a circular symmetry around the outside of our cylinder, but a set of parallel electric field lines along the length of the cylinder. That all okay? So let's talk about our first Gaussian surface. And let's make this a Gaussian surface that is, I think you guys would agree, a Gaussian surface that has the symmetry of a cylinder. So I'm going to place a Gaussian surface like this, some length around the outside of my cylinder. And I'm going to make it so that it is concentric with the cylinder itself. So if I was to go back, so my Gaussian surface, R. There's a couple things that, meaning this piece of the cylinder is being cut off from the rest of the cylinder by my Gaussian surface. And this piece of the cylinder has length h. Let me understand what I'm trying to talk about. This is a piece of the cylinder that's being cut off. It is inside my Gaussian here. Is there electric field lines that are passing through the top or the bottom of the can? I don't see any. The electric field seems to be left to right only. And the direction of the area seems to be up or down. That means that the dot product for the top is going to be E dot dA cosine 90 degrees. That's 0. No field lines pass through the top. And at the bottom, E dot dA cosine 90 degrees. Again, the direction of the area and the direction of the electric field are perpendicular to each other, so they have no flux passing through them. Are we good? That's why we chose a surface to look like this, so we can make it something that would integrate easily. So the top, 0, and the bottom, 0. At the same time, it'll be E dot dA cosine 0 degrees for all points on the sides. Because we know the electric field is outwards and the direction of the area is outwards all around the cylinder. So here, 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 the electric field and the area are all in the same direction. We good now? Keep going? Are we sure? Want to make sure. So, different dimensions like the top down and side view and stuff like that. And I'll ask you to draw what it would look like. But generally for stuff where you have to draw the Gaussian surface, they make it easier for you to draw. So they would not probably use the cylinder for when they would want you to draw the surface. Spheres, yes. They might ask you to describe the surface. And you'd have to say that I would use a cylinder that was concentric with the infinitely charged line or whatever. The word concentric should, become part of your vocabulary.